Good morning, everyone. Let us now see about the need for biasing. In order to operate the transistor in the desired region, we have to apply the external DC voltages of correct polarity and magnitude to the two junctions of the transistor. So this extra voltage which we are applying is called biasing. When we use DC voltages, okay, so when it is used as the voltages and it is used as a bias of the transistor, this biasing, giving an extra voltage with the help of DC voltage, is called DC biasing of the transistor. So let us see in detail about the analysis of DC load line. Consider a fixed bias circuit. So we have an NPN transistor, collector resistance, base resistance, or the biasing resistance. We have the input and the output capacitance. So consider this simple circuit. So C1 is the input capacitance, C2 output capacitance, base resistor, and the collector resistor. So we are going to now apply KVL to the input circuit or the base circuit. So when we apply KVL to the input circuit, so we have VCC, IB into RB minus VBE equal to 0. From this, we are now going to find what is IB. IB is VCC minus VBE by RB. So from the input circuit, we are finding what is the base current. And now we are going to apply KVL to the collector circuit. So in the collector circuit, when we write KVL, so consider this circuit. So we have VCC, ICRC, VCE equal to 0. So what is VCE? Is the collector to emitter voltage. So from the output circuit or the collector circuit, we are going to find the collector current IC. IC is VCC minus VCE by RC. So just now we are going to modify this equation 3. The equation 3 is same. Here the denominator RC we are going to write separately for the first term VCC by RC minus 1 by RC into VCE. So rearranging, so this equation is similar to a straight line equation y is equal to mx plus c. So considering the 2 points on the line, assume that VCE equal to VCC. So from equation number 4, assume that VCE equal to VCC. So if I assume first term will become minus VCC by RC, second term will be plus VCC by RC. So both will be getting cancelled. So the value of my collector current will be 0. So this will be considered as point A. When I assume VCE equal to 0, so the first term will become 0. So remaining I'll have only VCC by RC. So IC will be equal to VCC by RC. From that we get point B. So when we draw the output characteristics, so x-axis we have collector to emitter voltage and in the y-axis we have collector current. So what is point A? When I assume VCE equal to VCC is considered as point A, and when IC is equal to VCC by RC is considered as point B. So when I mark the point A and B and draw a straight line, that forms the DC load line. So this is a general characteristic curve. So we know that we have 3 regions. The transistor has 3 regions. Saturation region. So this region is termed as the saturation region. This is considered as cutoff. And here this is the active region. So from the graph, so this line, straight line, when you draw A to B, that line is called DC load line. So from the graph, if point Q is selected at point P, if it is selected at point P, then the transistor will work as an amplifier. If Q point is selected at point Q, then it acts as an oscillator. If Q point is selected at point R, it acts as a switch. Let us consider a small problem. So this is a simple problem considering the fixed bias circuit, beta value is given, base resistance value is 20 kilo ohm, collector resistance value is 10 kilo ohm. So here from the input circuit we are going to apply KVL. So if I apply KVL to the input circuit, I have VCC minus IBRB minus VBE equal to 0. We know the value of VBE, so always it is 0.7 volt. So I can calculate the value of IB. So if IB is known, I know that IC is equal to beta into IB. I can calculate the value of IC too. To find VCE, now I am going to apply KVL to the collector circuit or the output circuit. What is the equation KVL if we apply KVL to the output circuit? VCC minus ICRC minus VCE equal to 0. So from this equation, I can calculate the value of VCE. So I can calculate the value of VCE. So now I have to find the DC load line. To find the DC load line point A, I am going to consider VCE equal to VCC. I know that VCC is 5 volt. So VCE is 5. So here mark the point A as 5 volt. So first we are going to draw a graph mentioning x-axis as collector to emitter voltage, y-axis as collector current in milliamp. So here to find point A, VCE equal to VCC, that is 5 volt. So during this IC will be equal to 0. To find point B, IC is equal to VCC by RC. So we know the value of VCC 5 volt, RC is 10 kilo ohm. That value comes to 0.5 milliamp. So that is marked as point B. Now join the points A and B. This is the DC load line. To find the Q point or the operating point, we have to find the value of ICQ and VCEQ. So the value of VCEQ, we have found the value of VCE, or it is also as VCEQ to find the Q point. So that comes to 0.7 volt. So where is the 0.7 volt? So it just comes nearly here, 0.7 volt. Okay, so now we need to know what is ICQ. So we have also found the value of IC or the ICQ, that comes around 0.43 milliamp. So where is 0.43 milliamp? So it nearly takes this point. So if you join this point, this 0.7 volt and 0.43 milliamp, it comes nearly to this place, and this point is marked as the Q point or the operating point. So by which we are able to understand whether the transistor is in the whether it works as an amplifier, whether it works as an oscillator, or whether it works as a switch. So we can vary the Q point by adjusting the resistance value and then we are able to make the transistor to work in the desired region. So this is the need of biasing. Thank you.